Hi everyone. So in this video I'm going to go over the practice quiz 3. So it says list at least two methods used to reduce your exposure to HCl and HBr gas during the nucleophilic substitution reaction. So if you remember, the nucleophilic substitution reaction involved making a nucleophilic medium, which was sulfuric acid and ammonium chloride and ammonium bromide, and then you added that nucleophilic medium to undergo an SN1 reaction with T-butanol, and then undergo an SN2 reaction with 1-butanol. So that was the reaction that you did. And there was two things that you primarily did to do this. Now, for the SN1 reaction, where you actually had to reflux it, you used a gas trap. So a gas trap was a way of making sure that you collected that hydrochloric acid and hydrobromic acid as it was coming out of the reflux condenser, because these things are gases at room temperature, and with a gas trap you can dissolve them in water. The other thing is you added the H2SO4 to the ammonium chloride and ammonium bromide in the hood, because when you add a strong acid to molecules that contain chlorides and bromides, you can easily make hydrochloric acid and hydrobromic acid gas. So doing that in the hood so you don't breathe it in is really important. Another thing that you did do, I'm not going to write it here, is we use 7.5 molar sulfuric acid instead of concentrated sulfuric acid. And that's a more minor thing, but it does decrease the exposure to these types of gases. All right, question 2. Question 2 says, in the Grignard reaction experiment, glassware that was used at the beginning of the reaction is dried in an oven to remove any water present to ensure that any Grignard reagent form is not destroyed before it can be used to synthesize the final product. Draw the mechanism of the reaction that occurs between phenylmagnesium bromide and water to form benzene and some kind of magnesium hydroxide bromide salt. Okay, so the Grignard reagent, phenylmagnesium bromide, is the benzene ring with an MgBr attached to it. And this can react with water, which again, as it says in the question, you tried to get rid of the water, and the way we got rid of the water was we put things in the oven because the water doesn't stick to things that are hot. So this is basically what we have here. Now, how can these two things react? Well, what happens here is this carbon is partially negative. It's partially negative because it's attached to an MgBr. It's actually attached to a metal. So this partially negative carbon can attack one of the hydrogens of water, which is partially positive. So this partially negative carbon of the Grignard attacks the partially positive hydrogen of the water. And what do you get? Well, what you get is the ring now attached to a hydrogen. Of course, there's a hydrogen here, 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 and here that are not shown. But this ring attached to the hydrogen attached to the ring, I should say, is simply just benzene. What is the other product? Well, the MgBr is going to come off, and you're going to have an OH left. So you end up with an MgOH. BR kind of thing. Okay, so you end up with some magnesium salt that has a hydroxide and a bromine on it. So why did we get rid of the water? It's very simple. We wanted this molecule in the reaction that we did to react with benzophenone to form triphenylmethanol. If the Grignard reagent reacted with water, it would have formed benzene. Benzene will not react with benzophenone in order to form triphenylmethanol. So you have to get rid of the water because it will kill your Grignard reagent. This one says, in the first step of a Fischer esterification, the carboxylic acid is protonated by a strong acid. Using propionic acid, which is here, as the carboxylic acid, draw the three resonance forms of the protonated propionic acid. So basically, in this case, we have a 3-carbon acid, okay, for this esterification, like so. Now, note that both of these oxygens have lone pairs. and we add some kind of strong acid. Okay, probably H2SO4, but in this case I'm just going to put H plus. All right, so we have a strong acid here. Well, this is positively charged. Where are the negative parts of this? Well, the negative parts of this are the oxygens, specifically the lone pair on oxygen. And what's going to happen is the lone pair on this oxygen up here is going to take that proton. Okay, note that this oxygen is slightly more basic than this oxygen, so the protonation is going to occur on this oxygen right here. And what do we get? Well, these three carbons just go along for the ride the whole time. We now have double bonded to O, which is bonded to an H, and it only has one lone pair because one of the lone pairs is now this bond. Okay, this OH just goes along for the ride, and it still has two lone pairs. And what we end up with here, okay, is a positive charge on this oxygen. Now, one of the reasons that you could protonate here is because this positive charge can be resonance stabilized. So this could help to stabilize the positive charge. A plus charge on an oxygen, a more electronegative atom, probably is not ideal. So one thing that can happen is those electrons can shift there. And what we end up with is the three carbons. These three carbons are just going to go along for the ride the whole time. Now we have a single bonded to an oxygen, and now it has two lone pairs. The original lone pair it had plus one, this bond forms another lone pair. It's still bonded to an H. This didn't do anything yet, so it ends up like that. Now what do we have? Now we have carbocation right there. So the positive charge is here when this bond shifts. Now this positive charge can be stabilized by these pair of electrons going in. And what you end up with is a third and final resonance form. Again, three carbons just go along for the ride. This OH this time, the top OH, nothing happened to it. Now the bottom OH, it was single bonded, but now it's double bonded. So one of these lone pairs now forms a second bond. We have an H, and the other lone pair is just hanging out like that. In this case, the double bonded oxygen with the H on it is going to be the positive one. So in this case, we end up with three resonance forms that stabilize the protonation of this oxygen. And these are the three resonance forms that happen in the first step of a Fischer esterification reaction, in this case with propanoic acid. All right, so this is what it says. Is the product for an electrophilic aromatic substitution reaction shown below the correct product? So we have phenol, which is an OH attached to a benzene ring, and we add an electrophile. And we have to remember that what we're really looking at here is where this electrophile adds. So we have ortho, meta, and para. So we get a meta product. This is definitely not the right product. Why? Because this OH group is an ortho-para director. Now, it's very difficult to know whether this is going to be favoring the ortho or the para, but it's certainly not going to be favoring the meta, okay? So the meta position is definitely the wrong answer. Why? Because OH is an activating group. Activating groups activate the ring, and therefore donate electron density to the ring, and they want the ortho or para attack, not the meta attack. Let me show you the resonance forms that demonstrate that. So if we look here, if we have the mechanism of this reaction is essentially that this bond grabs that electrophile, okay? And what we end up with is the OH here, this lone pair and this lone pair, or excuse me, this double bond and this double bond, just go along for the ride. This double bond forms the new bond with the electrophile. But of course, there's still a hydrogen here, and there's still a hydrogen here. But you'll notice now, this carbon only has 1, 2, 3 bonds, and has a positive charge. Now, very much like in the previous question, this positive charge can resonate. So these pair can go here. And what you end up with is the OH is still here. The electrophile and the H is still here. I'm not going to keep drawing this H. All right, the double bond is now here because it jumped to here. This double bond, nothing happened to it, and now your plus charge is right there. And of course, this can resonate one more time, so this bond can go there. What you end up with, okay, the OH, the electrophile, and the H, the same positions. This time, this double bond didn't move, okay, but this double bond did. It's there. And now you end up with a plus charge right there. So when the electrophile attacks the meta position, the plus charge can be here, here, and here. Of course, if this were to go to the end product, which it won't in this case because of the meta position, okay, some base would come and remove this proton, and then this would come and reform aromaticity. So these electrons would reform a double bond after the proton is removed. But what's the problem? Why can't this go to the meta position? The reason is quite simple. This oxygen here has two lone pairs. And if you notice, this plus charge is never adjacent to this oxygen. If this plus charge were adjacent to this oxygen, you could draw another resonance form where these electrons donate electron density and the plus actually goes out into the oxygen. So you can think about it as oxygen is an electron donor. When you have an electron donor, you want the positive charge directly adjacent to the electron donating group. When you go to the meta position, that never happens. Now, I'm not going to spend the time to do it here, but if you draw this again with either the ortho or the para position, you will find in both cases you could draw a resonance form where the plus charge is directly adjacent to the oxygen, the electron donating oxygen. So the long answer is here. The shorter answer is that OH is an activating group and an ortho para director, and in this example we have a meta product, which is not the correct product for an activating group. This one says, draw the product or products formed by the following nucleophilic substitution reaction with 2-methyl-2-butanol, shown here. With an equimolar mixture of aqueous ammonium bromide and ammonium chloride in the presence of sulfuric acid, circle the major product, or if the products are formed in a 50-50 mixture, circle both products. Does the reaction go SN1 or SN2? All right, so we have a nucleophilic substitution. We have the nucleophilic substitution with the acid. So it's kind of a, where do you start with this kind of problem? But where I'm going to start this time is drawing the product. Eventually, I'm going to draw the mechanism because it'll make it more clear why we get the product that we get. But I'm going to start with just drawing the products. So the products are going to be a Cl substituting the OH and a Br substituting the OH. The reason you get both is because you have Cl- and Br- in solution, so it's going to substitute both. Now the question becomes, what is the ratio of these products? And it turns out that they should theoretically be a 50-50 mixture, or you could circle both of them as it says in the question. Okay, so it should be a 50-50 mixture. Why? Because this reaction is SN1. So now I've told you the answer. Okay, now let's look at the mechanism. So the mechanism, as is often the case, explains what's going on. Okay, so we have this molecule here. We have this in the presence of H2SO4, a strong acid. Now, OH is not a very good leaving group. Why not? Because it's a strong base. So in a lot of nucleophilic substitution reactions you've seen, the leaving group can just leave or get kicked out, depending on if it's SN1 or SN2. But the OH is not a very good leaving group. But it does have lone pairs and can grab a proton. And what we end up with is this protonated alcohol with a plus charge on the water. Now the water is a very good leaving group, all right? It's a weak base, so it is a good leaving group. So with alcohols, we have to protonate them before we can have the leaving group. Now the question becomes, does the X minus, the 50-50 mixture of Cl minus and Br minus, does that come in and kick this out? Or does this just leave on its own? And to figure that out, what we need to look at is the carbocation that would be formed. So if this leaves on its own, in this case, we're going to form a tertiary carbocation. When you form a tertiary carbocation right here, so it would have 1, 2, 3 alkyl groups and would be a tertiary carbocation, the tertiary carbocation is stable enough to form. So in this case, the leaving group leaves, the water leaves. And what do you end up with? You end up with this carbocation right here and water as your byproduct. Now, this carbocation is in the presence of a 50-50 mixture of Cl- and Br-. Although this carbocation is stable enough to form, said another way, this is an SN1 mechanism, 1 because it only depends on the rate of formation of this carbocation. It doesn't depend on the nucleophile. Okay, this carbocation is stable enough to form, but it's also extremely reactive. So it's going to react with the first thing that it runs into. So it has a 50-50 chance of hitting a Br- or a Cl-. So if it runs into a Br- first, by coincidence, it'll form the bromo product. If it runs into a Cl- by coincidence, it will form the chloro product. Remember, in chemical reactions, it's not magic. These things actually have to touch each other and interact with each other in order to go on to form product. So if it hits this 50% of the time and this 50% of the time, we get a 1-to-1 mixture. The reason for that is this is an SN1 mechanism, so the rate is only dependent on the formation of the carbocation and is not dependent on the strength of the nucleophile. Why is it SN1? Because this forms a tertiary carbocation. Said another way, you have a tertiary alcohol to begin with. Thanks for watching this video. I know I gave more details in the video than on the answer sheet, but I just wanted to make sure that I gave a full explanation to hopefully clarify the concepts as well as answer the questions. Thanks for watching.